Hi, I'm Ben-Yaakov. This presentation is entitled Transformer Leakage in LLC Converters. There are two key videos that are relevant to this presentation, and here are the links. And I'm going also to print the links on the YouTube page of the video that you are now watching. The videos are very important because they give the theoretical basis of what I'm going to discuss in this video. So we are talking about an LLC converter which has two inductors, a resonant capacitor, usually there will be a transformer, and here is the rectifier in the output section. The LM inductor is many a times part of the transformer. It's basically the magnetization inductance of the primary. LR many times is a external inductance, but in some design there is an attempt to use the leakage of the transformer as the L sub R or part of the leakage and then some additional inductance. The question that I'm posing in this presentation is what is the proper equivalent circuit to use when you have a non-ideal transformer? The point is that if you have coupled inductors, which is the general case with some mutual inductance, you can represent it in many ways, and this is shown in the videos that I've referenced. You can show it with the leakage on one side, the leakage is on the two sides, actually it could be on this side too. Also there is this option. In fact, there are infinite possibilities here. The question is, which is the one that you should use when you are simulating or analyzing an LLC converter? It would appear that the right one is this one, because here is the resonant inductor, you might say. This is the parallel inductor. So this seems to be the more proper one. If you use this one, well, it seems to be a problem here. Here is an inductor, and here are going to be diodes, so there may be some interaction. So maybe this is not the right way to go. But as I've shown in the two videos, and in fact in some other videos, all coupled inductor models are equal in terms of the voltage and current transfer ratio and terminal impedances. So you can use whichever you want. So this means that any model can be used when analyzing or simulating LLC converter. It does not matter. The result would be exactly the same. Now, which one would you like to use? Really, you can use any one. Usually you'll pick a one that simplifies the analysis, the simulation, or the understanding of the circuit. So if you put the inductance on this side, then it's kind of more intuitive to understand the interaction of these inductors with the circuit, with the resonant capacitor. However, if you use this model, the results will be exactly the same, both analytical and by simulation. Now, since I've posted the videos on this subject, I got many comments of people who just don't believe it. They say, no, if you have an LLC, you have to put the inductor on one side, the leakage on one side or the other side, otherwise you'll get improper results, and you should do it in a very specific way. So this is the purpose of this presentation, to convince the unconvinced. I mean, finally we have to accept the fact that you can use any model that you want. So here is how we are going to do it. We start with a coupled inductors. These are coupled inductors. There is a nominal coupling coefficient of 0.896, and we have no inductance here. This is just a coupled inductor. Here we have a rectifier, and this is the output section, and this is the resonant capacitor. The operating frequency of this converter is about 100 kilohertz, plus minus, of course, depending on the load and the ratio between input and output. So this is the very basic, fundamental representation of the coupled inductor. And then I did a transformation and represent the same unit, the same magnetic unit, by this model, which has the parallel inductance here and the leakage here. So this is one of the options. I'm then representing another option in which the inductance, the leakage inductance here, Lm is also here, and here is just a winding here of this ideal transformer. This is an ideal transformer. I didn't say it earlier. This is also an ideal transformer, okay? And this is the Lm, and this is the leakage. Now, the ideal transformer is formed by coupled inductors, which have a coupling coefficient of 1 and very large inductances, okay? And the inductances were made large by multiplying them by a very large number, 10 to the fifth in this case. So the ratio is the correct one, but the inductances are very large, so this is an ideal transformer, and these are the inductances per the model that represent the original coupled inductor. And now I'm going to run all of them together, and I'm going to probe in all of them the input current, which is a sensitive parameter, the voltage on one of the rectifiers here, and the current, and this is done for all of them. Okay, so I'm going to probe for all of these, the input current and a voltage and current of a output diode, which are very sensitive to changes in operating point. And here is the first run. Switching frequency is 120 kilohertz. This is the input voltage. This is the input current. This is this current, but this, and this all together, and as you can see, they are superimposed. They're exactly the same, no different. This is the voltage of the diode. Again, these are the three diodes, exactly the same. And this is the current of the diodes, and again, it's exactly the same. Okay. Now, I did some step analysis, stepping the frequency between 80 kilohertz, 110 to 120, three frequencies. Again, the green is the input voltage, which is the same, of course, the same excitation. This is the input current for the three frequencies, and these are the three current superimposed, one on the other, exactly the same. And this is the voltage on the diode, the three diodes. That's not the three diodes, this is three frequencies, and each one of the curves here is the three diodes superimposed, and this is the current of the diodes. Again, they're exactly the same. And then I did the sweep of the coupling coefficient, 0.5, 0.8, 0.95. Again, they are exactly the same. Notice that for the high coupling coefficient, that is the low leakage, there are some oscillation here, probably between the inductance and the capacitance of the diodes. But notice that it's exactly the same for the three, okay? So again, these are the three diodes. Each of these curves is three diodes superimposed, the voltages, and here are the three currents superimposed. So clearly, it doesn't matter which model that you use, all of them, if the transformation is correct, will give you exactly the same results. Now, what about the case that you have a split secondary? Well, the situation here is more complex, because you have a coupling coefficient between primary, secondary, primary and the other secondary, and then between these two. These coupling coefficients are very important, and the transformation is more complex. And this is something I'm going to cover in a forthcoming video. So this brings me to the end of this short presentation. I hope you have found it of interest, and that all of you are now convinced that in the case of a non-ideal transformer, you can use any model that you want for the leakages, if of course you do the transformation correctly, and all of these models will give you exactly the same result. And the reason is very simple, because the models are giving you the same transfer ratio, voltage and current, and the same impedances. So from outside, you cannot distinguish between them. So it doesn't matter what's happening inside, the terminal behavior is the same.